Okay, so we're going to talk a little bit about human vision, specifically defects in human vision. Now, there is a definition we need here, the near point. That's the closest distance at which your eye can focus clearly, say for a reading distance. And that's typically taken to be 25 centimeters. So your near point is 25 centimeters. Your far point, that's the greatest distance that you can see clearly. And for a young and healthy eye, that's an infinite distance. Now, the human eye works by focusing light onto the retina. So that focusing happens in two places. It happens on the outer curved surface of the cornea, and the cornea is responsible for about half of the focusing. Then there's a pupil, and the light makes its way through the pupil and then passes through a lens, and that's responsible for the other half of the focusing. In our discussion today, we're just going to focus on the lens part of that. And so what will happen here is that light rays will pass through the pupil, and then at the back of the eye, if the lens and cornea do their job, there'll be a clear image here on the retina. The retina is just a tissue here at the surface of the back of the eye where the image is created. So that's inside view. In front view, this is what it looks like. Here's the lens of the eye. Here's a ring of muscle, and then there are these little ligaments that connect the lens to the muscle. And we'll see that that is what enables us to focus. Because for an object that's a long way away, and the rays of light are essentially parallel coming into our eye, the muscle relaxes and gets a little longer, and as it does that, it pulls the eye lens flat. Now, when the lens is pulled flat, it doesn't bend light very much. As a result, there's not a lot of bending here. And let's try that one again. Yeah, so not a lot of light bending. And for that distant object, we get a nice, clear image on the back of the retina. All these rays are focused at a point, and so you get a clear image. Now, when the object is closer, we strain the muscle, we use the muscle, it gets shorter. As the muscle gets shorter, the lens will bulge. As it bulges, it bends the light more. So in this way, for an up-close object, we again get a nice tight focus here on the retina. So this is what the lens looks like when you're viewing something distant, a relaxed muscle and a flat lens. This is what it looks like when the object is up close, a tense muscle and a bulging lens. And in both cases, we have a nice clear image with the three rays meeting at a point on the back of the eye. Now, of course, that situation doesn't last forever, and eventually your lens loses the ability to accommodate and change in shape. At that point, you have a vision defect and you need a corrective lens. These lenses are prescribed on the basis of their power, and the power is just the reciprocal focal length. So if you had a 50 centimeter focal length corrective lens, that's 0.5 meters, 1 over 0.5 is 2, so your prescription would be 2. And it can be 2 positive or 2 negative, depending on whether you have a focusing lens or a diverging lens. Let's examine 2 common vision defects. First of all, nearsightedness. Now, when you're nearsighted, that means you could see near things but not far things. And the reason for that is that your lens remains somewhat bulged even when you're looking at a distant object. Now, you want a bulgy lens when the object is close, but when it's far away, you want it to pull flat. If your lens remains bulged, then it's going to bend the light too much. And for this distant object, you'll have a clear focus here, not on the retina. By the time the light reaches the retina, it's all spread out. It'll be a blurry image here on the retina. So because this lens no longer pulls flat, it remains bulged, so for a distant object you don't see clearly. So the way we correct that is with a diverging lens. This can be in your glasses or on your contacts directly against your eye. What that will do is it will take these parallel rays coming from a distant object and it'll spread them out a little bit, because that's what diverging lenses do. And then when you've got the increased focusing power of this lens, the diverging lens sort of compensates for that extra bulginess of the lens by diverging the rays a little bit so that you get a nice clear image on the back of the retina once again. Now, calculation-wise, we speak of the far point. So if you're nearsighted, your far point is no longer at infinity. It might, say, be at 200 centimeters. That means the furthest distance that you can see clearly is 200 centimeters. So if you had an object that was quite distant, say at your ideal far point, which should be an infinite distance away, what you want to do is wear a corrective lens so that the corrective lens puts an image where your eye can see it at your actual far point of 200 centimeters. Now, this will be a virtual image with a negative image distance. So we'll just use the mirror lens equation. Ooh, that's a little bit untidy. Let's try that again. So the mirror lens equation, there we go. So the object is at infinity, because that's the one we want to be able to see. The image of the corrective lens will be at our actual far point, which is 200 centimeters, and because it's a virtual image, that's a negative image distance. And we want to solve for the focal length. Well, reciprocal infinity is just 0, so solving, we see that the focal length is minus 200 centimeters, or minus 2 in meter units. So the power is 1 over 2, or negative 0.5. So that would be your prescription, a minus 0.5 for that nearsightedness. And so now a distant object, the lens puts it where your eye can see it, and you will see it clearly. Another common vision defect is farsightedness. That's where you can see far but not near. The reason you can't see near is that your lens doesn't bulge enough. It remains flat. So then when you've got an in-close object and you need lots of focusing power, you don't get it. You don't get enough bending so that the rays of light create, say, an image here and behind the retina, and here on the surface of the retina, it's all spread out and blurry. It's not nice and tightly focused. So what do we need to do here to fix this? Well, we need a little extra focusing power of a converging lens. So now, in-close object, well, this first lens bends the light a little bit, and then this weaker bending power of the second one is therefore compensated for, and with the first little bit of bending and then the second bit of bending, you get a nice clear image on the back of the retina. So if you had a farsighted person then, and your near point was only 150 centimeters, well, that means that if you put something like a book at the ideal near point, which we defined before, which was 25 centimeters, you want to be able to read it. So your corrective lenses are going to create a virtual image where your eye lens can read it at your actual near point of 150 centimeters. Now, because this is a virtual image, our image distance will be negative. So we apply once again the mirror lens equations. So our object, say our book, 25 centimeters from our eye, we will create a virtual image 150 centimeters from our eye so that the lens in our eyes will be sufficient to see it clearly. So solving over a common denominator of 150, that's 6 minus 1 over 150 is reciprocal focal length. So that's 5 over 150. That's 150 over 5. That's 30. Positive 30 centimeters for the focal length. The prescription is the reciprocal focal length. That's 0.3 meters. So 1 over 0.3 is 3.3 plus for your prescription for this farsighted student. So those are the common vision defects and how we address them, and an explanation for that using both the ray drawing and also using calculation.